Hello, everyone. My name is Ariam Gutierrez. I'm a partner solutions architect at AWS, and I'll be talking to you today about microservices on AWS. In today's session, we will be covering what are microservices and when to use them, how to go from monolith to microservices, how you can deploy microservices on AWS, and how microservices communication happens, how you can actually communicate those microservices. So let's start from the beginning. What are microservices? Microservices are small independent applications that are loosely coupled and they are independently deployable. They usually communicate each other using language agnostic APIs, and they are owned by a single team who manage its lifecycle. This is quite important because you need to be aware of that when you approach or you switch to microservices, it not only implies a change in the way you design application or architecture, but also in the way your team is structured and how your team talk to each other. This is a famous phrase from Melvin Conway. He said that any organization that designs a system will inevitably produce a design whose structure is a copy of the organization's communication structure. So again, approaching microservices is not only a technical topic or matter, but also an organizational structuring. Some of the benefits of leveraging microservices are, for example, agility. Microservices foster an organization of small, independent teams that can take ownership of their own services. Those teams can act within a small and well understood context, and they are empowered to work more independently and more quickly. And that actually shortens the development lifecycle. Another benefit is simpler deployment. In microservices, you only deploy small components rather than a big application. So if you want to bring features to production, you only have to deploy a small parts of your application, those microservices. Um, Another benefit is flexible scaling. In microservices, when you design for microservices, you can actually scale just those microservices that requires more resources rather than in a monolithic environment when you actually have to scale the entire application, right? In microservices, you only scale the component that need more resources. Another benefit is technological freedom in microservices because of those components are independent one from each other. You can leverage the tools, frameworks, programming languages that fits better for each microservice. So there is no one rule for all, one technology for all your microservices at all. Like it was like in the way it is in a monolithic environment when you actually leverage the same tools for the whole application. Here you have a wide range of options and you can choose whatever fits better for you. Another benefit is reusable code in microservices because of you develop those independent components. You can then reuse them in another application, in another system you might be developing in the future. So you can leverage that effort as well. And finally, resiliency is the latest benefit we want to mention here. Though because of you develop microservices, independent components, right? A failure in one of those components doesn't necessarily need to imply a failure in the whole application. In a monolithic environment, if something fails, right, it's very likely that the entire application will fail. It is not the case in a microservices world where you can actually scope and isolate the issue faster, and that issue in one microservice won't expand or affect the whole application. So another phrase from James Lewis, he said that microservices buy you options, right? The options are the benefits we were mentioning before, right? But there is a cost of that. There are pain points you need to be aware of. For example, when your company you start approaching microservices, you will see that there is very likely you will see an increase in the cost at the beginning, especially because teams they don't know exactly how microservices work, and they will spend some time experimenting, and that will result in a cost, especially at the beginning. The new organizational structure, the one we were mentioning before, right, will slow down the company, especially at the beginning as well, up until those teams understand their context, how to work independently, and how to communicate each other. The company speed will is very likely is going to slow down. Also, another pain point might be the technology overload of having a whole new set of tools and technologies to master. So each team will need to learn their own tools and technologies, the one they have to put in place for their own microservices. And another team will use another set of tools. It doesn't necessarily need to be the same one, right? And it takes time for those teams to and bandwidth for those teams to master those new tools. Finally, the developer experience is different. Running locally often is more complicated, and some services need to be run in the cloud for allowing communications. So who should and shouldn't use microservices? So first things to mention here is that microservices is one architectural approach. It is not the architectural approach, right? So there are several options here, and this is just one of them. So microservices might not be a good fit for companies with a small group of developers that they don't understand the concept behind, not only from a technical point of view, but also the changes they need to put in place in the organization's point of view, right? So it might not be the proper moment, the good moment for them to start leveraging microservices. On the other hand, if you have a wider group of developers, they are well grouped into different teams, and they understand the concepts and the implications of leveraging microservices. Probably this is a good fit for them. Usually, we see that the biggest constraint is usually people, right? So in microservices, one service can be hosted in a container, another can be in a VM, another in another kind of technology. So that change in the mindset, right? It takes time to understand all the tools and options you have and how you can apply whatever fits better in each case. This is completely different from a monolithic environment. So let's discuss now a little bit how to go from monolith to microservices. I have an example here of a monolithic architecture. This is an application that has several components. For example, it has a storefront UI, have different services like account, cart, and shipping services. And also all these services and components are leveraging a single database, right? As you can see here, this is one deployment unit. Often in these kind of scenarios, there's one code base for everything. Communications between services go through function calls in the programming languages, and this is all tightly coupled, right? If something fails in one of those services, it's very likely that the entire application will fail. If you want to scale the application, you have to scale the entire application as a whole rather than independent services. So how you bring this architecture to a microservice? Well, how it will look like, right? So this is the same application, but in this case, we have broken down that big application into independent components. First of all, we have the storefront, which is the user interface, right? And the interface with the end user. And then the storefront will do the proper API calls to the relevant services. For example, the account service, the cart, or shipping service. Each service or microservice will have its own database, so that ensures that the entire microservice is unique and completely independent and deployable from the rest of them. And if, for example, one of those services, let's say the cart service is failing, only that service is going to be affected, not the entire application. The rest of the services will keep up and giving service to the end user, right? So you may be wondering now how this actually look like in AWS, right? So I have an example here of a microservice on AWS, a way of deploying a microservice on AWS. This is, we have three tiers here. First one is user interface, and here we are leveraging Amazon CloudFront and Amazon S3 for the user interface. And then we have the layer of microservices leveraging Amazon API Gateway and AWS Lambda. AWS Lambda is where you are going to host the code of your application. It's a fully managed serverless compute environment. You just put your code there and we run it for you. And then finally, we have a data store layer. It can be either Amazon Aurora if you are leveraging MySQL or Postgres, for example, or DynamoDB if you are leveraging a NoSQL database. This is, again, this is in this environment, this microservice is fully elastic. You pay on demand, and it's completely serverless for you. There is not, you don't need to manage any kind of operating system or infrastructure underneath. But what if your teams still they have experience with Docker containers and they want to keep leveraging Dockers? So for that, we have an option which is based on AWS Fargate. AWS Fargate is another serverless compute layer on AWS that allows you to host your Docker containers, right? You basically say which is the Docker image you want to use, and we run it for you. And the rest of the components of the architecture are basically the same. This is, again, all of this is totally serverless. There are going to be a couple of sessions afterwards. If you want to dive deep on AWS Lambda and AWS Serverless, I advise you to watch those sessions. So let's discuss now a little bit about microservices communication, right? There are two ways of communicating. First one is synchronous communications or systems, and asynchronous systems. So when it comes to synchronous systems, some characteristics is that they are tightly coupled. Usually a problem in a downstream service or system can have an impact in the upstream caller. And for example, there can be a timeout, there can be a delay, or things like that can actually affect the upstream caller. And what actually happens is that it's very likely that the upstream caller will retry. And those retries will actually fan out and amplify the problems in the downstream services, right? So you need to be aware of these drawbacks of leveraging synchronous systems. We usually say that some things simply, it takes too much time to wait, and you don't have to wait for everything, okay? And some systems are asynchronous by nature, and you need to be aware of that, and you need to have options for overcoming these issues. So, for example, here I have an example of an application called Wild Ride Unicorn. At AWS, we like unicorns. So this is an application that leverages a synchronous communication system. In this case, a unicorn will take you from point A to point B, and once the ride finished, the application will notify the ride management service saying this was the user, the customer, the distance, and the time it takes to do that ride, right? The ride management system then, before confirming or responding back to the application that initiate the request, have to call back to a group of backend services like customer notification, customer accounting, loyalty, and others services. It needs to let them know that the ride finished for those backend services to do their job. In the meantime, the user is still waiting, right? But what if one of those services, for example, the loyalty service, is failing, right? Or the ride management system will probably retry, and those retries will amplify the issue in the backend service. At the same time, the user is still waiting. Just when all those services finish their job and notify to the ride management system that everything is okay, right? It is when the ride management system will flag the ride as completed and will reply back to to the original request from the user. So the whole process takes time, right? So we have several options for overcoming or working around those issues. For example, one is circuit breaker. This is a pattern, right? So in this pattern, we basically have two services. The order service, for example, wants to communicate to the payment service, and in between we have a circuit breaker. The circuit breaker maintains a status of the circuit, and it basically ensures that when for example, in this case, the payment service is alive, it keeps the circuit closed. But if the payment service is failing, it will open the circuit, and the order service won't be available, won't be able to reach the payment service, and the request will fail, basically without retries, without waiting times, and so on. So, for example, in this case, if the payment service, for example, is failing, circuit breaker, like I said, will open the circuit. The order service won't be able to reach the payment service. In the meantime, the circuit breaker will keep trying periodically to query to reach the payment service up until it is alive. Once it is alive again, the circuit breaker will close the circuit, and the order service will be able to reach the payment service. Then this way you avoid, you reduce the idle time from the caller, and you avoid those unnecessary tries that can actually amplify the issue in the backend. But how you implement this on AWS? On AWS, you can leverage AWS step function for this. This is an example where you have a function called getSecretStatus that is actually going to query Amazon DynamoDB. In Amazon DynamoDB is where you are going to store the state of the circuit, the state management system, right? So the getSecretStatus will query DynamoDB. It will ask it whether the circuit is closed. If the circuit is closed, it will actually execute the random function, and the communication will happen. If the circuit is open, it will basically fail. It will trigger a fail, and that's it. The original service that is trying to reach the backend service won't be able to do it, right? We have avoid in this scenario, in this architecture, we have avoid the retry part of the circuit breaker, just for simplicity, but there are examples on how you can implement it. So let's talk a little bit about asynchronous communications now, right? We have how to exchange messages, right? First option is something called one-way, right? One-way is when you have a sender and a receiver, and you basically want to send a message from point A to point B, right? There is not a response, so the sender is not expecting a response from the receiver. It is just sending a message through a message channel, and that's it. The receiver will receive it. Another option is called asynchronous request response. So in this case, we have a requester and responder. The requester sends a message through the message channel, but it is waiting. It waits for a reply from the responder, right? So in this case, the responder needs to know who sent the message for being able to reply back, and you need to keep a correlation between the two messages. You need to be able to correlate the message A with the replies in the message B. So the first option is usually called integration pattern, right? And the second one is usually called conversation pattern. This is a conversation between two parties. When it comes to message channels, we have an option called point-to-point queue. In this case, we have a sender and we have receivers, right? And we have a queue in between. Basically, the sender sends messages to the queue, and then the receiver will start pulling the queue. Each receiver, each message is going to be pulled and processed by just one of those receivers. So the message is not going to be received by more than one receiver. And you can use the queue, for example, for buffering purposes. If you have a peak in your application, the queue will help you to buffer that peak of messages. And also you can leverage the queue for scaling the amount of receivers you have, right? So you can scale and deploy more receivers if the queue is growing, for example. Another option is publish subscribe topic, and in this case, we have again a publisher and a subscriber, and the publisher will send messages to a topic, and the subscribers will subscribe to the topic. So in this scenario, all subscribers will receive all the messages and process all of them. And in this case, there is not a buffering concept, so you cannot buffer. If one subscriber is failing at the moment that a message arrives the topic, that subscriber won't be able to receive the topic. So you need to be aware of that. So you need to understand the two flavors or options here and apply whatever fits better in your case, right? So when it comes to AWS, there are two options. Here, I mean, for a point-to-point queue, you can leverage Amazon SQS, Simple Queue service. It's a cloud-native and serverless service. For the publish and subscribe, you can leverage Amazon Simple Notification Service, Amazon SNS. Again, also it's cloud-native and serverless. Both services, you can consume both of them through an API. Both services can act as an event source of AWS Lambda. But what if you are restricted to using industry standard messaging protocols like JMS or AMQP, right? So for that, we have Amazon MQ. Amazon MQ is a managed implementation of RabbitMQ or Apache Active MQ. Amazon MQ support both scenario, point-to-point or PubSub. And Amazon MQ can also be act as an event source of AWS Lambda. So let's step back to our synchronous communication application, the wild ride unicorn. So how we can overcome those issues we already mentioned about synchronous communication. So for example, in this case, we could add an SNS, we can leverage SNS and put SNS in place in between the ride management system and the backend services, right? So in this way, when the wild ride unicorn app notifies that the ride was completed to the ride management system can send the message to the topic, and can reply back to the application confirming that the ride was completed and recorded. And then the ride completion topic will notify all the services, and they will do their job by their own. But this still have an issue. What if for example, the loyalty service is failing? It will lose the message, it will lose information. So for that, we can leverage a pattern called topic queue chaining, in which you mix the PubSub and the queuing pattern. You can deploy SQS in between SNS and the backend services. So in this case, it's similar. When the application notifies that the ride has completed, the ride management system sends a message to the topic and replies back to the original user, right? The topic, instead of executing or calling directly to the backend services, will put a message in the SQS queue of each of those services, and then those services will put the message and process it. If one of those services, for example, the loyalty one, is failing, doesn't matter, the message will still be in the queue when the loyalty service comes back alive, right? So you first save time from the user, so you don't put the end user and the whole system on hold because something is failing in the backend, and also you don't lose messages in between, right? So sometimes you need to do a transaction that expands across multiple microservices, right? In this case, we are using as an example a flight booking application, and there are a number of steps that needs to happen up until you actually reserve your booking. There are several steps, several microservices that need to be called, right? And the transaction itself will expand across over all of them. So in a traditional environment, leveraging a relational database, you will be using something called two-phase commit, right? The two-phase commit is made of two phases. The first phase is prepare. In the prepare phase, there is a coordinating process that requests all the participants in the transaction to promise to commit or roll back the transaction. In the commit phase, the coordinating process actually commits the transaction. If a participant can't agree in the prepare phase, the transaction is basically a rollback. So this is how it actually happens. It usually happens in a relational database world. But in a distributed system, you cannot leverage the two-phase commit approach, right? So for this, we have a pattern called Saga pattern, right? The Saga pattern, there are two ways of implementing Saga pattern. The first one is called choreography. In choreography, services, each service will react to events of other services. There is not a central orchestration, right? And each service reacts on failed events from previous service. So each service know what they have to do if a previous service failed, and they know what they have to do to roll back the whole transaction. So another way of implementing Saga is called orchestration. So on AWS, you can leverage AWS step function for implementing this model, right? This pattern. In this pattern, we have you will have a central orchestration of the whole transaction. This is what you are seeing in the right hand of this slide, leveraging AWS step function, right? You will have the central orchestrator will know all the steps that has to happen for completing the transactions. Those are the yellow boxes at the right? And the orchestrator also knows what it has to do if some of the steps fail. If one step fails, it knows what it has to do for rolling back the entire transaction. This is usually called preventing transactions, actions, if possible. As you can see, there are some an architecture like this and a scenario like this is more complex. The application flow is more complex than the patterns we have seen before, but still you need to be aware of this pattern just in case you need it for your application. So finally, I'm letting you hear some resources we have used for preparing this deck. Microservices.io is quite good. You can find there a number of other microservices patterns, and you can dive deep on those if you wish. There's also a white paper called Microservices on AWS. This is something we came up with, and it helps you to bring the microservices concept to the AWS environment. And also in this QR, you can have direct access, quick access to serverless LAN patterns. This is a website where we are publishing all the time serverless patterns you can leverage for your application. There are a number of them. So this is all what I have for you today. I hope you learned something new in this session, and I will be available for the next 5 minutes for questions and answers. Thank you so much for your time, and I hope you enjoy the session.